Hello chemistry students, my name is Adam Kozlowski and today I'll be teaching you about the equilibrium constant or uppercase K. And so first up, you have to understand that uppercase K, the equilibrium constant, is not the same as lowercase k, which is a rate constant in chemistry. So you have to understand that these are not equal. And so you'll know because, well, despite meaning entirely different things, uppercase K, or what we're working with today, has no units. It's a naked number. There's no units on it, while lowercase k will. So that's the first thing. Don't mix these two up or it'll end very poorly for you. So the equilibrium constant is used to represent a ratio of products to reactants in a given reversible reaction. So that means that if a reaction is going both forwards and backwards, or using its products to create reactants, and using its reactants to create products, what it means is that in this reaction, what will happen is when these two rates equalize, we can represent the relative concentrations of the product and the reactants using an uppercase K value expression. And so the way you would write out this particular K value expression, or any K value expression, would be by putting the product over the reactants. So let me elaborate on how the products are represented in the K expression. So what we'll put here is the concentration of product C to the power of little c, or the coefficient, or the amount of moles of product C in the equation. And then we'll have product D to the power of D. And what you'll do is you'll put that over your reactants. So reactant A, concentration of reactant A to the power of A, or your amount of moles of A, times reactant B to the power of B, or your amount of moles of B. And so one trap fall that you have to watch out for is that while this is the general rule, you have to watch out for the states of matter in the reactants in the products. If something is aqueous or gaseous, it'll appear in the K expression. But if it's a liquid or a solid, it will not take part in the K expression. You'll just leave it out and only include the aqueous and the gaseous elements from the reaction. So that's something to watch out for. And we'll see that in the next segment. So let's put what we've learned to practical application with a real equation. So here we have ammonia reacting with water. And so if we were to find our K value, we'd represent it as so. NH4 plus from the from the product times the concentration of OH minus, and this would be divided by NH3 from the reactants. And so you'll notice that H2O, or water here, isn't included, and the reason why is because it is in the liquid phase. And as you have learned previously, only aqueous and gaseous elements or reactants and products will be included in your K value expression. So I'm going to go ahead and make up some values here just for demonstrative purposes. So let's just say this is like 0.4 molar. This is also 0.4 molar. Something like that. This is 1.2 molar. The way that we could find our K expression is, let's just get our calculator here. We just concentration of NH4, 0.4, times concentration of OH, 0.4, divided by our concentration of NH3. And so as you can see, we'd get a rather low K value. And so the way you could interpret this is you could interpret your K value when it's less than 1, the reactants are favored. That means that there will be more reactants than product at equilibrium. And and so clearly here we have more reactants than we do have products. And if K is greater than 1, that means we have more product than we do reactants. And if K is equivalent to 1, then we have equal amounts of product and reactant. Thanks for watching my chemistry explainer video.